Hello, and thank you for being here. My name is Alex Reed. I'm co-founder and president of Fluence Analytics, and I'm excited to be talking to you today about our real-time analytics technology for the polymer industry. One of the things that we're particularly interested in with real-time analytics is to truly transform business in a number of areas. So one of the key priorities that we've seen a lot is cost. So customers looking to reduce their operating expenses and gain their market share through a competitive advantage. Yield is another big push, getting more and more out of your assets, doing more with less. And then on the quality side, being able to put out the same product every time to all your customers and also develop new products and standardize that quality within a very tight specification globally. That's another very big push. And then finally, operator exposure, waste reduction, environmental footprint. Anytime we can use our feedstocks and materials more intelligently, we're making an impact towards sustainability. A little bit about who we are. We're a spin-off from Tulane University. We have maintained some R&D operations in New Orleans. We recently moved to Houston, Texas in 2021. As you could see, a significant amount of technology investment, a number of patents, both issued and pending globally. And our team is very much R&D engineering focused. So we have a lot of people that are developing the hardware, the software, deploying these systems and doing applications with our customers. And as you can see here, we are a venture-backed company. We raise capital from Energy Innovation Capital, Diamond Edge Ventures, which is the venture group for Mitsubishi Chemical Holdings, JSR Corporation, and Yokogawa Electric. And our mission really is to deliver products that help our customers produce their products better. So everything from the hardware and software sensors required to optimize production. So some of the issues we saw in the industry are around this problem of manual sampling. We see visiting plants all over the world that in the polymer industry specifically, there is still an extremely heavy reliance on manual sampling of the process to analyze critical properties of interest. So what that means is either at the end of a batch or every hour, every 2 hours during a continuous production cycle or semi-batch production, there are operators taking samples, taking them to a QC lab where then a technician makes sample prep and measurement, sometimes several measurements. And then you have data that is typically hours old, then sent to the control room either to take a very conservative control action or just see what you made in the batch. Now, that's not to say this process doesn't work. Obviously, our modern lives are impacted by polymers as they're found everywhere. However, there is some inefficiency when you don't have real-time information about the properties of interest, which is fundamentally what our customers, polymer manufacturers, are selling to the end users, how those polymers will perform in that final application. So we've seen this. This is very standard and fairly well-known issue in the industry. So looking at what that directly impacts, if you think about quality, you look at in a continuous production, off spec from grade transitions or deviations from steady state. In batch or semi-batch, you're looking at just not hitting the target you wanted after your full production cycle. And what that leads to is rework. So maybe you have material that you blend with other products, good product, to get an average product you sell to a customer. Or you are altering your production style and schedule to minimize some of the issues that are known in transitioning materials or campaigning certain batches. So that leads to excess inventory that if you had better control and more dynamic optimization, you might not need. On the quality side, this we've actually seen within plants, same reactor, same operator, same feedstocks, different product comes out, then imagine if you take that globally, where you have different feedstocks, translated SOPs, different skill sets of the operators, and the equipment everywhere is completely different. So being able to replicate quality with all of these changing variables is a key point, and can be quite challenging. So that's where more dynamic control or dynamic measurement can be helpful. And then on the control side, we're looking at opportunities for enhancing visibility. So right now, we've heard a lot of people say that it's a bit of a black box. They are flying blind, and they don't quite understand exactly what parameters affect what outputs. And if you do want to understand it, it can be quite a time-consuming endeavor with a lot of your R&D resource for modeling single reactors to truly map out what is happening within that product. And then on the efficiency side, obviously, if you're looking to scale up, crank out new products, change different recipes, target very specific applications, that scale-up process can be slow and difficult. Break-ins in production can be quite time-consuming if some of the issues aren't worked out. And then there's quite a bit of lab work you need to do there, or even tracing problems. So what we've developed is ACOMP, which is Automatic Continuous Online Monitoring of Polymerizations. And at a very high level, this is how it works. We're continuously extracting from the reactor. We have conditioning and measurements all happening in an automated system this inside of our enclosure with multiple sensors. And then we have proprietary software that takes that raw data and computes those parameters of interest to our customers, which then goes to the control room where controlled decisions can be made. So as you can see in the process, what this means is 30 to 50 times faster data, 36,000 more data points per hour. If you think about, you get one data point per hour from the lab versus one every second from online. So basically, the amount of information available to the operator, the human in the loop, is orders of magnitude above where we are today. And if we think about what that impacts, you saw the costs and the effects of that lack of data. So if we really break it down, how do we translate that to value? We're talking about cycle time reduction and freeing up capacity. We're looking at reducing need for certain analytical testing over time. We're looking at avoiding degradation of product and off-spec production. And then we're thinking about where we can impact this waste environmental footprint. So the manual sampling, emissions, those are exposures. So those are safety concerns for operators and plant personnel. And then anytime we reduce consumption, and we've seen ROI in the less than 1 year, in one case 6 months, for delivering on a few of these different areas. And if we look at what we can work in, so this is not a tool we can use everywhere today. We do have a roadmap to cover as much of the polymer industry as we can. As many of you know, this is an industry that has everything from commodity, high volume plastics, all the way to low volume specialty, high value batches for semiconductors or electronics or certain adhesives and paints and coatings. So it is quite a diverse industry, and so we do have a roadmap to cover as much of it as we can. But today we're particularly focused on anything that is in a liquid or melt phase, and that's where we can do most of our measurements. And then we also, for other systems, maybe we can't make all of the measurements, but we can track certain other key parameters. So that is where, if we engage with you, we can assess your application, some of your objectives for optimization, and see where our technology solution fits. So here's a few case studies. This one was in the SSBR styrene solution styrene butadiene production. Here are the process conditions at the bottom. So what we have is, this is the second phase of a reaction using real-time ACOMP data. So what we're looking at is molecular weight, the reduced viscosity, and then we have a proprietary high shear viscosity measurement where we intentionally will shear the molecules as they pass through our viscometer. So getting additional information about architecture and things of that nature. So what we're particularly interested in here is the trend of the molecular weight and the viscosities as you build up the first stage of the production, the polymer. And then in the second stage, where there's a coupling step, seeing the efficiency of that coupling going from step 1 to 2, and looking at some of these ratios and even optimizing when to take this step. So there's quite a few advantages of knowing the properties as you approach that critical next step of the reaction. And then obviously, if you're thinking about it, if you don't have extra steps, how you can use that product to or that data to know when your batch is done if you're targeting a very, very specific molecular weight or viscosity, for example. Looking at gelation, so this is we have a way to assess at a very sensitive, very, very low concentration sensitive way the onset of events like gelation. So this was a step growth or a polycondensation reaction where we actually were able to see, so as you see here, we were tracking it over time with molecular weight, and then we were looking at the light scattering signatures, and all of a sudden you see some spiking towards the end of the reaction. This was well before it was visibly gelling, but it did end up gelling, so we had an early alarm, if you will, of that gelation event in this process. And then if we look at continuous production, you see here, basically, as I noted before, this is an EPDM example. The objective is to make product within, in this case, it's a Mooney viscosity, which we've correlated to a molecular weight, and they try to target very specific window of Mooney in production. This is very standard in this industry. So here you see this gray line would be your midpoint, that middle of the spec target you want to stay at. Ideally, if you could get there as quickly as possible and stay there for the whole production run, you'd be making perfect product. So that is what we're targeting if you look at it. So the big benefit here is this grade transition. Either you go out back to a solvent and build back up, or you do a transition from one grade to another. Either one, that evolution from whatever the previous condition was up to that next target property grade, doing that as quickly as possible minimizes your off-spec production. So here, as you can see, this time from this spec to the next one, those are, in some cases, can be many hours of off-spec production. And if a lot of times that control is driven by, or at least validated by offline data points taken every 30 minutes, every hour, every 2 hours. So you can imagine that the control properties are, in some cases, fairly conservative, or control algorithms used to drive those processes are fairly conservative to account for the fact that there is a lot less lab data. So the advantage here is having real-time information allows a faster path to get and know when you're in spec and target to get to spec. And then once you're at steady state, so say you're producing at this midpoint, anytime you saw a steady state deviation out of specification, then you would know based on the real-time information and take corrective action. This is actually the complete data set with the raw data of that SSBR run. So the first time I was showing very focused on the molecular weight properties and the evolution of the reaction towards the last stages, which was, if you looked at it in this section of the process, here you see the full run. So this, if you look at other types of batch or semi-batch applications, this is how we track conversion. So we're actually looking at the monomers converting into polymers here through, in this case, the UV signature. That's the monomer being consumed over time, and then our calculated conversion value based on that raw data. And then, as you would expect, as your monomer is building into polymer, you see your polymer mass, whether it's from viscosity, light scattering, or even the shear viscosity, building up over time. So this is a very good visual representation of how you can see the evolution of the reaction and have that information available for control or assessment of a completion of a batch. And then here, this is a case where we were doing residual monomer chasing. Our target was to get down, in this case, the customer was a specialty manufacturer, had a lot of different grades, that their products that they produced in each reactor. And so what we were looking for was a way to understand dynamically the endpoint of the reaction. So typically in those high mix production environments, customers will have very standardized SOPs. In some cases, it's almost standardized to the least common denominator based on the equipment in the entire global plant network or in that plant. So you might have a very specific set of conditions that you run for, say, 12 hours to complete each batch, no matter what happens. In this case, what we were able to observe is that given a lot of the variability, which I highlighted earlier, that you see in batch production, the feedstocks, the operators, the equipment, all those different things that can change, the reality is that you're going to hit whatever your target specification or specifications are at different points. The kinetics will vary reaction to reaction. And so what we saw was that on average, if you use the dynamic endpoint, some cases you were done several hours sooner than the standard SOP. Some you were very close to the standard SOP. But on average, if you did it across many batches, the savings was, I think in this case, 15 to 20%, maybe 17%. So that's what this represents here. This is the normal recipe, and this would be the stop point based on a dynamic endpoint averaged over all the batches. The other thing we noticed in this case was one of the key metrics or items that properties that this customer was selling to their end users was the molecular weight, or determined by the viscosity, intrinsic viscosity. And so what we saw in some batches was when it was completed sooner, so when the kinetics were faster than expected, and that residual ppm property was achieved, which would be at this point, these represent the offline ppm versus the continuous, that molecule actually, when you were in that reactor with temperature and shear from the impeller, actually degraded over time. So large chain molecule under those conditions eventually would actually degrade a bit. So in order to follow the recipe, there was actually an impact to the quality, which was unexpected. We were mainly targeting residual monomer so that we could increase cycle time, and saw a quality benefit as well. This was a quote from our customer. They were particularly interested in the cycle time, as we highlighted here, but they also highlighted that the quality was a very interesting side benefit of that analysis. A little bit more detail about how the technology works. So as we mentioned before, we're continuously extracting a very small stream from the reactor. will go anywhere from 0.05 to multiple milliliters per minute. And that actually comes into our ACOMP front end, where we've developed a fully automated set of sample preparation and sample conditioning equipment. And then we use either a process solvent or a different solvent to get that polymer stream continuously through our process into a very low concentration, which we then flow continuously through our detection, which is typically the intrinsic viscosity and shear viscosity, the UV and the light scattering. In some of the lab cases, we also have the refractive index. And then we get that continuous raw data, which we analyze. And as you see here, our properties are our outputs: molecular weight, intrinsic viscosity, composition in certain cases, total monomer conversion, total residual monomer ppm, and then obviously with the evolution of the process, any detection of process anomalies we would see as well. So looking at the ROI, I mean, the place where we saw, or where we're driving most of our initial value to customers is really this bottom, the capacity and reducing analysis and improving yield. Quality we see in some cases is developed over time. Some cases it's immediate because that's the biggest pain point. But then we really see a lot of value being created as we launch or help our customers launch new products and deploy those into production. So a couple examples would be in the batch and semi-batch process. So this is a fairly large-scale batch production. The key point here is a small impact to that cycle time based on that residual monomer or key molecular weight specification would be significant. So 5-10% impact would be noticeable and would certainly give a less than 1 year ROI. And then on the continuous side, the off-spec reduction, this is mainly what I was saying before with the steady state deviation or the enhanced changeover control. So those are a lot of the benefits that we've seen for the different use cases. Now, as we deploy more of these systems, as we generate all this real-time data, we see a tremendous opportunity for leveraging that information to do feedback control. And so we have developed some technology in this space. And basically what we're looking at is taking that real-time data on the properties of interest that are being manufactured and then sold to end users for performance in applications. We're looking at that real-time property data and then actually designing control algorithms to partner with the control system that would actually perform feedback control action to drive towards specific properties. So basically dialing in performance characteristic in the end application and making each production run, batch, whatever it is, specifically as close to that specification as possible within a very tight window. So that feedback control based on data we view as a huge opportunity. As we get more of these systems out there, we partner with our customers to improve this control algorithm and then deploy it further into production. Here's actually a case we did in the pilot scale with that controller. So here on the left is a traditional polyacrylamide reaction with the batch process is this blue line. This would be your natural trajectory as your polymer, your molecular weight evolves over time during the polymerization. And then here is the setup we use. So this is your typical ACOMP control or ACOMP system with the extraction, recycle, and then all the mixing and analysis. Here were all the different parameters that we were able to control in that reactor: the impeller speed, heat, cool, adding chain transfer agent, initiator, monomer, oxygen, nitrogen. So we had all these different knobs we could turn. And so the idea was, given we were targeting a molecular weight, how could we change each of these knobs to improve the control of the reaction? So this would be the process controller, the software that we wrote that did those actions. In this case, we were adjusting monomer and initiator feeds. And here you can see the results. So in order to show a very, very different trajectory than what would be the natural path, we actually had a set point to increase the molecular weight throughout this is weight average molecular weight, increase it throughout the reaction. And so we had a target set point, and then as we were running and feeding real-time data into our controller, we would very quickly assess any kind of deviations and then adjust feeds to the monomer or initiator to drive it along that set point. As you can see, it followed it very, very, very well. So this was, very rapid cycles of tuning and control, and it did factor in flow rates and delays and things like that. So it was very interesting, and this is what we're talking about when we see the opportunity to control properties of material into the future as we deploy more of the base, the measurement technology that I spoke about earlier with ACOMP. Another area we see opportunity is data contextualization. And so here, if you look at a typical plant, there's a control system with a lot of real-time process information. You have a process historian, which has a lot of information stored. So most plants have just terabytes of data that they could access over many, many years. And so combining these things with the context of the real-time properties is huge, because then we can actually look at which process condition in real time, and then as we look at historical data, which of the process conditions affected and created certain results for properties. And then you have the feedback that you can then correlate to other lab data, so you can build advanced correlations over time to a number of parameters. If you have real-time properties, real-time regular sensor data, temperature, pressure, feed rates, combined with that lab, all of a sudden you're looking at very interesting mix to optimize over time. And then troubleshooting. So if you have any kind of quality issue, as indicated by the measurement technology, tracing that back to whatever it was in your feedstocks or anything in the ERP, for example, that you could then identify as the reason for that and get to the issue faster. And then just to sum this up on the applications, basically a lot of the end-use applications, so a lot of the materials that we're working with are elastomers, water-soluble polymers, some engineering plastics, adhesives, paint coating applications. So there's a lot of different polymer materials that go into these. So those are particularly of interest today, and we are under different development projects working with certain customers to expand into applications that we're not working in today, as I noted before. And then batch, semi-batch, continuous. So we worked in all types of conditions on processes and solution, emulsion, bulk. So whatever the conditions are, those are of interest to us to at least see if we can work with companies to help them optimize. And so pulling it all together, today what we're offering is a real-time data set that's never been generated, and we believe, based on our customer feedback and data we've had in the field, that it adds tremendous value in the optimization of production. Some of the key benefits, as I know before, are the production yield, the quality aspects, reducing off-spec, the increasing capacity, launching new products faster, reducing the worker exposure, so safety, and then all of our targets, which are to minimize energy consumption, raw material waste. And so with that, I want to thank you for your time and your attention, and I do look forward to any questions or feedback, and we would love to hear from you if you're making polymers and are interested in digitalization and optimization. Thank you.